This is a very common setup for a projectile motion lab, and I want to go through all the calculations with you. Let me show you the actual setup. So I took this, we have this ball launcher, and I launch it from the table. It was a little bit above the table to the ground like this. Let me just show you that, and then we're going to use that to find the launch velocity of the ball, and then we're going to use that launch velocity to predict where it's going to land if we shoot it at an angle. So switching over here, here is the setup. Move this over a little bit so you can see. Here's the launcher up here. So I measured the height of the launcher above the table right there, and then I'm going to launch the ball. And actually, I've already played a little bit, so let's just back up a little bit. And it's in slow motion, so there's a little bit of weird effects from the lights and stuff like that. But I'm just going to scroll through. So you pull the launcher, pull it. And then I put a string on the ball just because I thought it'd look cool. And I don't think it really made a difference in the trajectory. And then you can see where it hits. And there's a piece of carbon paper down here, so I can actually mark exactly where it hit. Now notice that I want to measure from the bottom of this. So this marker right here shows you where the ball was launched. If I'm measuring the X distance, I want to measure from that center, right? Because that's where the center is going to hit. And then you can see it hits right. It's about 0.5. It's short right there because the meter stick needs to be moved over. I just had that meter stick there in case I wanted to do video analysis later. I always like to do that. You can always scale the system and things like that. So here I measure this height and this distance. Now, you may think, hey, I'll just measure the time. And I'm going to talk about the time. But let's just imagine, let me play this in slow motion speed. So you see right there is still a good second or so. And that's at 240 frames per second slow motion, so it's slowed down, I don't know, by a factor of 4 or something like that. And so this is a super short time, and that's important. Okay, but let's go ahead and write down the measurements and see how you would actually calculate the launch velocity 2 different ways with this. So there are 3 things I can measure. I can measure, let's call this the launch position. Right down here, I'm going to call that the origin. So at t equals 0, then I have x0 equals 0, y0 equals this distance above here. Now, also, you'll notice I'm measuring from the bottom of the ball to the floor because I want to know how the center of the ball doesn't hit the floor. The bottom of the ball does. Okay, so that y distance, I wrote it down, is 0.25 meters. And then I shot it, and it went a distance from this distance. Actually, that's the start of the ball right there. Let's just say this distance, x final is going to be, I measured it as 0.5 meters. And then let's say delta t, I measure something. I don't know what that is. I don't want to write it down because I don't want to disagree with other stuff. But let's say, how do you deal with projectile motion? We define projectile motion as the motion of a ball or an object where the only force on it is the downward gravitational force. And so we can't have air resistance. We can't have the launch of this thing. We can't have the collision with the ground. It's all right after it leaves the launcher till right before it hits the ground. That's projectile motion. Now in this case, if I call this the y direction and this the x direction, you can see that there is no force in the x direction. The only force is in the y direction. And since this force depends on mass, this gives me the 2 things. The x acceleration is 0 meters per second squared. The y acceleration is negative g, where g equals, this would be negative 9.8. Negative g is negative 9.8 meters per second squared. And that's because the masses cancel. So if that's true, you'll notice that this acceleration does not depend on y. Doesn't depend on anything, it's 0. This acceleration does not depend on x. So what we get is 2 independent equations of motion. I can look at the motion of the ball in the x direction independent of its motion in the y direction. So if that's the case, then in the x motion, I really only have the one following kinematic equations. I'm not going to go over the kinematic equations. I'm just going to write them down. So I have this kinematic equation. X equals x0 plus vx0 t. Assuming x at t equals 0 is x0. This is the initial x velocity, which doesn't change. right? So this means that if I shoot the ball horizontally with some initial velocity 0, its initial velocity is in the x direction. So in this case, shooting it horizontally, only in this case, v0 is vx0. So if I solve for vx0 up here, then I can get the launch velocity. So let's solve, if I also put x0 equals 0, like I said, then I get, I'm just going to solve it. This is going to be equal to x over t. And now be careful. I put a star. That's just using these variables. Really, the x velocity, it'd be better to say delta x over delta t. I hate writing that. That's just the way it came out up here. It's really x0, x minus x0. I'll write it over here. X minus x0 over t minus 0, because I started at t equals 0. But x0 is 0. So suppose I measure this time. Suppose in real life the time is 0.2 seconds. I'm just making up a number. Let's say delta t is 0.2 seconds. And you timed this with a stopwatch. You could get the velocity. But the problem is that if I time that with a stopwatch and I go start, stop, I mean, I'm going to get a wide range of values, right? Because timing something that quick is really difficult. So if I'm off by even 0.1 seconds, so I go from, maybe at my range is from 0.1 to 0.3, that's a large difference in velocities, okay? And so I really, it's not a very good method to get the time. So instead what we can do is to get the time from the vertical motion. So if I know that this ball starts from rest at a certain position, I can write down the following for the y motion. So in the y motion, I have the final y is initial y plus the initial y velocity times time plus 1/2 at squared, but that's going to be minus 1/2 g, right? Because a is negative g t squared. So that's your kinematic equation for the motion of an object in one dimension. Now, in this case, what is my final y position? 0. What is my initial y position? Well, that's just a value. I'm just going to leave that as y 0. What's my initial y velocity? If I shoot it horizontally, then initially the y velocity is not up or down. So the initial y velocity is 0. So this is going to be 0 times t minus 1/2 g t squared. Well, 0 times t is 0, so that whole term goes away. So now I have a very simple equation. I'm going to add this term to both sides. So if I add 1/2 gt squared to both sides, I get 1/2 gt squared plus 0 is just 1/2 gt squared, and that's going to be equal to y0. Now I want to solve this for time, so I'm going to multiply both sides by 2. I get g t squared equals 2y0. I'm going to divide both sides by g, and I get t squared equals 2y0 over g. And then I'm going to take the square root of both sides. T equals the square root of 2y0 over g. So that's really important. That's my time. I can use this time up here. Okay. So let's go ahead and put in our values. And I don't even need to, you could calculate the time and then put that in. I'm going to put it all in at once. I'm going to say v0 equals x, which I measured, times divided by this. So it's going to be divided by g over 2y0. So let's put in our values. I get x distance of 0.5. I'm going to leave off the units. Square root of 9.8, that's positive 9.8, divided by 2 times 0.25, 0.25. And my calculator. I lost my calculator. I like that calculator. I mean, I don't really like calculators, to tell you the truth. Oh, here it is. There. Okay, let's plug it in. Clear. So I'm going to say 0.5 times the square root of 9.8 divided by parentheses, because you don't want to do divided by 2, right? And then multiply by 0.25, because it'll do that wrong. 2 times 0.25, or you could just put 0.5, because 2 times 0.25. Parentheses equals. And I get 2.21 meters per second. Okay. Now suppose that I take that same situation and I shoot it at a 60-degree angle. So here we have the same launcher. And we're going to assume that the launch velocity, the magnitude, does not change with angle, which isn't practically true, and it's not exactly true either, but it's close enough. Now, I found that this particular launcher, let me show back over here, and I think this is just a problem with me. This is an older launcher, and I find that when you shoot it completely horizontal, the ball doesn't quite sit back against the plunger. There's a spring in there to push it, so there's a little space, and so you get a tiny little collision. So during that collision right here, between the ball right there and the plunger, it loses some speed. So it actually goes a little bit slower if you shoot it horizontally than if you shoot it at an angle. Because if you shoot it at an angle, the ball sits back against that plunger. I think later models have a magnet to hold it in there. It works a little bit better, but that's just me. So it's still a pretty good experiment. Okay, so let's launch this at an angle theta. And so it has some initial y position, y0, and it's going to go through the air, and then we want to know where it starts at, again, x0, and we want to find the final x. Now you'll notice in this case that if I shoot it up, it should be in the air for a longer amount of time. So you would think that would make it go further. But now my x velocity is only a component of this. So that's the first thing we need to do. If I launch this at some angle v0, at some angle theta, then I have vy0 and vx0, right? I have to find the x and y components of that initial velocity. So using my normal trig functions here, if I take the cosine of the angle, then that would give me the adjacent. So I can say vx0 is v0 times cosine of theta. And then I can do the same thing with the sine. vy0 is v0 sine theta. Okay, so now I have to do that in terms of the angle. So let's write down our x motion equation, and just like we did before, x motion, x equals x0 plus vx0t. That's it. Now, instead of vx0, this is just going to be a number, right? I just found the launch velocity. v0 equals, what did I say it was? 2.31? 2.21. Yeah, 2.21 meters per second. That's important. And then I know theta, right? So you could just write down this as a number. I'm not going to put the number until the end because that's kind of the way I like to roll. So I could write this as x0, which is 0, but I'll write this as x0 plus v0 cosine theta times t. So that's the same thing. I just put, instead of vx0, I put v0 cosine theta. Again, I'm trying to find for this final x. I know the initial x. I know v0. I know theta. I just don't know time. Okay. So in order to find the time, I'm going to use the y motion. So here I have y motion. Again, I have the same equation. Y equals y0 plus vy0t, the initial y velocity, minus 1/2 gt squared. I'm going to go ahead and put in my y velocity. Again, I know that it's just a number, but I'm going to write it as an equation. So it's going to be, let's rewrite the whole thing, because this one actually really matters. So the final y is going to be 0, right? Because it ends up right down here. So let's say 0 equals y0, and then my initial y velocity is going to be plus v0 sine theta t minus 1/2 gt squared. Now, I know y0. I know that. I know everything, right? So it's just a number plus a number times t minus a number times t squared, and I want to solve for t. So I have a problem here because I can't do what I did before. I can't get t by itself and take the square root because I have a t term there too. So if you have a little experience solving these kind of problems, you'll see that this is a quadratic equation. And so I have to use the quadratic equation to solve it. So remember, in general, the quadratic equation says if you have something of the form 0 equals a x squared plus b x plus c, this is how they write it all the time. Then x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so in this case, we have, instead of x, we have t. And then we have, this is going to be our a, this is going to be our b, and this is going to be our c. So, and this will solve for the times. And we will get 2. Okay. So let's just go ahead and put our values in for a, b, and c, and then we'll plug it into the quadratic equation and get 2 times. Okay. You could do it without that, but it gets a little messy, and I think it'll be more useful to do it as numbers. So let's say a is the term in front of t squared. So I have 9.8 times negative 1/2. So that's going to be negative 4.9. If I take 9.8 divided by 2, I get 4.9. So a is negative 4.9. Let's put a box around that. B is going to be the term in front of x, which we're doing t, so it's the term in front of this. So it's going to be v0 sine theta. So I need to calculate that. So let's go up here and say 2.21 times the sine of 60, which I could have done without that, but that's fine. And am I in degrees? Yes, I'm in degrees. And I get 1.91. And again, I'm going to leave off the units. It would be in meters per second. And then finally, c is my constant term, and that's just my initial position. And I launch it from the same height, so it's 0.25 meters. Okay, so now let's calculate T1, right? We're going to get 2 times because I have a plus or minus. So I'm going to do the plus first. So T1 is going to be negative b, which is this, negative 1.91 plus the square root of b squared. I'm not going to put the negative because I don't need to. 1.91 squared minus 4 times a, which is going to be negative 4.9. So it's going to be plus 4.9. I had a negative times a negative. And then c is 0.25. And then take the square root. And then all of that's going to be divided by 2a. And then a is negative 4.9. So it's going to be, and multiply by 2, I get negative 9.8. So let's put this in our calculadora and say clear. Let's see if we can do this. I'm going to put parentheses, right, to make sure that I add these before dividing by that. So I'm going to say parentheses negative 1.91 plus square root 1.91 squared plus 4.9, I missed the 4, times 4 times 0.25. And did that have a parentheses in the square root? I think it did. Okay, I might have messed this up. And then the top, and then divide by negative 9.8. I don't know if this is right. Okay. And I get negative 0.103 seconds. I think that's right. Now for T2, I'm going to do the exact same thing. I'm just going to change that to a minus. Okay, so I'm not going to rewrite it. So I'm going to clear. So let's say parentheses negative 1.91 minus the square root. Yeah, I need to put that parentheses there for me. 1.91 squared plus 4 times 4.9 times 0.25. Close parentheses for the square root, close parentheses for the fraction, divided by negative 9.8 equals. And I get 0.4, that seems too small, 0.493. Oh no, I guess it's okay. That's right, because I shot it at an angle. Okay. So, just as, you know, mathematically what's happening here is we're solving for the roots of this parabolic equation. Where does it cross the y equals 0 plane? And then we have that point, and then we have this point. And so it if you go back in time, it looks like it came from the ground negative 0.1 seconds ago. That's what that time means. Okay, now this time, you'll notice this time is larger than the time before, even though I didn't calculate it, because it has to go up and then back down. Okay, so now that we have the time, we're going to use this time, and then we can use this equation to solve for the final position. So I know, let me write down V0 equals 2.21 meters per second. Theta equals 60, and then I'm going to say T equals 0.493, 0.493 seconds. So X equals x0 plus v0 cosine theta t. So x0 was 0, so it's just going to be v0 2.21 times cosine of 60, which you don't have to do the calculator, not going to worry about though, times 0.493, and we get our total distance traveled, clear 2.21 times cosine 60 times 0.493. And I get 0.54 meters. That's how far it should go. Okay, now I'm going to show you the, let me show you the actual run. Okay, let's see, I have it right here. Just so you can see what it looks like. Okay, so here's the launcher. It's at a 60-degree angle. I'm just going to scroll through in slow motion, because it's in slow motion. And there's that string, which I don't think really matters. And this is the actual mark. But you'll see it goes a little bit farther. It's actually still pretty close. It goes a little bit further because, like I said, in this case, I'm pretty sure the ball sits in the thing and it has a better launch velocity. I'm going to make an experiment to measure the change in velocity as an angle and see if I can find some cool stuff with that. But that'll be another experiment. So this one missed, but I think it's okay, and the calculation is important. Now, let's talk about one more thing. What if I wanted to include uncertainty in the calculations? You know, especially over here for finding the launch velocity. So let's say that I measure this and I measure that. Okay, so let's say this is plus or minus. If I measure the height as plus or minus half a centimeter, so 0.005 meters. That seems realistic. Maybe even I don't think you'd say plus or minus a centimeter. That's pretty large error. Half a centimeter is still probably too high. I mean, I think the meter stick that I use went down to a millimeter anyway. So you could have this much smaller. But still, that's that. This distance right here, if you launch it a bunch of times, you're going to get a little bit different values. So this one, you could say plus or minus based on the variation and where it lands, the standard deviation. But what I want to really talk about is how would you calculate that final velocity with uncertainty? So let's say that I'm just going to make up a number here. Let's say 0.01 meters. It's not that. Okay, it's not that. But now let's say I calculate my launch velocity. So, if I go back over here, I'm going to write down the important things. I'm going to write down actually this, right? We already calculated that from this. So that is just V0 equals X times the square root of G over 2Y0. I did it all in one step. Now to calculate the uncertainty, I'm going to use the crank 3 times method. So that means I calculated the velocity already as 2.21 meters per second. Now let's calculate the minimum velocity, V0 minimum. What would I do to get the minimum velocity? Well, I'd put in the minimum x, right? So it'd be x min, not x min, x min. Okay, there's no Wolverine here. That's just a Marvel joke because I like Marvel. Divided by the square root of g. I'm going to assume is constant. And then 2y0 max, right? Because I'm dividing by y0, putting in a larger value here would give me a smaller launch velocity. So this is going to be x min is going to be the x position, which was 0.5 minus 0.01. I'm not going to do the whole calculation. I'm just setting it up. And then times the square root of 9.8 times 2. And then I'd have the 0.25 plus 0.001. And that would give me my minimum. Now when I go to calculate the maximum, V0 max velocity would be x max divided by the square root of g over 2 y0 min. And I would put in the, because I'm dividing by that. And that would give me my max velocity. And then my uncertainty in the velocity would be delta V0, V0 max minus V0 min over 2. And that's how you would do that. Okay. Now, what if you want to calculate the uncertainty in the final position? Where did it go? I had 3 sheets of paper. That's strange. Okay. Well, in that case, it'd be a little bit more complicated because you have a more complicated equation. You have 2 values. You have an uncertainty in the launch velocity and uncertainty in the launch position. And so you have to do a lot more work to get the uncertainty. But it's not impossible. So, okay. That's projectile motion. Hopefully that's useful to you. That's it.